Hey everyone, this is the fourth video for section 5.1. So this is the last video for section 5.1, and we are going to keep talking about divisibility. So last video, we justified some of the divisibility rules, but before we did that, over here, this example 2, we justified a divisibility rule for 12. And so we're going to do that again, but for 24. So just to remember, I'll write it down here. So a divisibility rule for 6 is divisible by 2 and 3. And a divisibility rule for 12 is divisible by 3 and 4. Okay. So, sorry, I can't draw that. Okay. So these are the two rules that we have that kind of can motivate this, because in the second video, we made a rule for 12, and to make that rule for 12, we had a rule for 6 that we based it on, and 24 is right, we have 6 times 2 is 12 times 2 is 24. So we can kind of venture that this will be similar. So we remember that we got the rule for 12 by looking at ways to multiply to get 12, and similarly for 6. So we have that 2 times 3 was 6, and 2 times 3 is 6, and 3 times 4 is 12. So let's think about the ways to get 24. So we can do 1 times 24, we can do 2 times 12, 3 times 8, and 4 times 6, and then we start repeating 6 times 4, 8 times 3, and so on. Okay, so we're trying to get this to be a similar pattern. So we are trying to make a rule for 24. We want something to be divisible by 24 if it's divisible by one number and another number. Okay, so 1 and 24. So a number is divisible by 24 if it's divisible by 1 and 24. Well, that doesn't help us at all, because everything's divisible by 1, right? You can divide anything by 1 and get no remainder, because you just get that thing back. And then 24 is not going to help us, just because we're trying to make this simple. We're trying to make a rule for 24 in terms of the factors of 24. Okay, well, what about 2 and 12? Well, 2 and 12 might work, but let's think about how we came up with these rules for 6 and 12. We talked about this concept of overlap. So 6, the only multiples of 2 and 3 that are shared are the multiples of 6, right? The multiples of 2, 2, 4, 6, 8, 10, 12, and then the multiples of 3, 3, 6, 9, 12. The only multiples that those share are 6, 12, 18, 24, and so on, the multiples of 6. Similarly for 12, when we think about the multiples of 3 again, 3, 6, 9, 12, 15, 18, 21, 24, and the multiples of 4, 4, 8, 12, 16, 20, 24, the only multiples those share are 12, 24, 36, and so on. So what multiples do 2 and 12 share? Well, because 12 is odd, every multiple of 12 is a multiple of 2, because this is exactly the same discussion we had when talking about making the rule for 12, that every multiple of 12 will be even, right? 12, 24, 36, 48, 60, and so on. All of those will be even. So every multiple of 12 will be a multiple of 2. So that's not going to help us, because there's a lot of overlap there, right? We want the only overlap to be the multiples of 24, but it's all overlapping there. Okay, 3 and 8. Let's think about the multiples of 3 again. 3, 6, 9, 12, 15, 18, 21, 24. Okay, and the multiples of 8, 8, 16, 24. So that one seems like it could work, right? The only multiples of 3 that are shared with multiples of 8 are the multiples of 24. So this one might be able to work. Okay, what about 4 and 6? So the multiples of 4 are 4, 8, 12, 16. And the multiples of 6 are 6, 12, 18. So these share not only the multiples of 24, but the multiples of 12. right? 12 is a multiple of 4 and 12 is a multiple of 6. So they don't have too much overlap. Where, although they have less overlap than our other examples, they do share multiples of 4 and 6. Sorry, let me think about how to say this. The numbers that are both multiples of 4 and multiples of 6 are the multiples of 12, not the multiples of 24. So this one has a little bit too much overlap. So 3 and 8. So our rule for 24 is that a number has to be divisible by 3 and 8. Okay, so that can be a rule for 24. Again, if you want to challenge yourself, think about a rule for 48. Feel free to email me to ask about this, but can you think of a rule 48 using its factors, or 36, or any other number you can do things like this for a lot of numbers, but we are only going to talk about in the videos 12 and 24, just so it's a little bit easier. Okay, so for the last part, we're going to talk about divisibility in different bases, just because we talk about different bases a lot, and I don't believe this is covered in the book, but I just wanted to talk about it just because, I don't know, we tend to do things in different bases a lot. So just so we kind of have a comprehensive view of everything. So we want to look at 430 base 7. And we want to figure out if it's even or odd. Well, in base 10, if you're kind of thinking in a base 10 mindset, 430 base 7, you may look at it and be like, yeah, obviously it's even because it ends in a 0, 2, 4, 6, or 8, right? But let's think about what this means. So let's write this in expanded form. So 430 base 7 is 4, 3, and 0. So I'm actually, before I write this in expanded form, I'm just going to draw it with base blocks. And so this, we have 0 units, we have 3 longs, and we have 4 flats. So, right, which is the 1s, the 7s, and the 49s place. Okay, so if we draw this, we have 4 flats, and 3 longs. Okay, so we want to know if it's even. So even meaning divisible by 2. So we want to be able to take this and make 2 even groups. So this is another way to think about even, are making 2 groups that are even. So if we split this, well, let me make it red. So if we split this down the middle into 2 even groups, well, we have 1 extra long on the top. So if instead we take that long and we make it into 7 units, we can have 3 on top and 3 on bottom, but then we still have 1 left over. So this is actually not an even number, even though it ends in a 0, because we want to take it and be able to split it into 2 equal groups, 2 even groups. And you can also see that by writing it in expanded form and converting it to base 10. So this is 4 times 10, 7, 4 times 7 squared, plus 3 times 7, plus 0 times 1, which is 4 times 49 should be what, 90? No. 4 times 49 should be 196. Yeah, 196 plus 21 is 217. So this is actually 217 base 10. And when we look at it in base 10, it's really easy to see, yeah, this is odd. But we want to kind of be able to have some intuition about even and odd and divisibility in different bases. So you can kind of think of it like so. Like, rather than does it end in a 0, 2, 4, 6, or 8, think about what it really means to be even, and it just means to be a multiple of 2, right? Divisible by 2, a multiple of 2, same thing. Can we split it into 2 equal groups using these base blocks? Okay, so example 8. We want to kind of generalize this and make a divisibility rule for 2 in base 7. So let's just start off by listing some of, well, the numbers in base 7. So we've done this before. So we start off with 0, 1, 2, 3, 4, 5, 6, and then we increase. Right, we carry when we get to 6. So it's 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and then we repeat with 2s, and then 3s, and that's as far as we'll go. Okay, so we want to think about which numbers are even. We're going to look at which numbers are divisible by 2. So the first ones start off the same: 0, 2, 4, and 6, right? Because these numbers just represent that value. They just represent that value. So then 1, 0 represents the value 7, so that is not divisible by 2. 1, 1 represents the value 8, which is divisible by 2. 1, 2 represents 9, which is not divisible by 2. 1, 3 represents 10, which is divisible by 2. And 1, 5 represents 12, which is divisible by 2. But 1, 4 is 11, and 1, 6 is 13, so they're not. So by this point, you can start to kind of see a pattern that, just like, right, even and odd are concepts that can be applied to any base, and every value alternates being even or odd. It's either divisible by 2 or it's not, where it's divisible by 2 if you add or subtract 1. So this pattern continues where 2, 0 is 14, 2, 2 is 16, 2, 4 is 18, 2, 6 is 20. And I would like to point out kind of at this point that although I'm saying, right, that 2, 6 is 20, that we represent 20 in base 10 as 2, 0. But the value 20 is different, right? It's like this. It's a word. It's an English word. It's not 2, 0. 2, 0 is how we have chosen to represent this in our base 10 society, but 20 is a value, and 17 is a value, and 33 is a value, not necessarily a number. We often write it as a number, but 2, 6, base 7 represents the value 20. So I just kind of wanted to make that distinction right here, that the value is this English word, and we just represent it by these Arabic numerals. Okay, so we can see that just like normal, every other value is even and every other value is odd. So the ones that are boxed in are these even values. So think about what patterns you notice. So on the first row, it's 0, 2, 4, 6, right? But then we get into 1, 1, 1, 3, 1, 5, and the values on that row look like, right, they all end in an odd digit, right? 1, 3, 5, and then we're back to 0, 2, 4, 6, 1, 3, 5. So think about it. There could be a lot of different patterns, just like in chapter 1. There can be a lot of different patterns that you notice here. But one rule that we can devise is by looking at the sum of these digits. So if the base 10, right, so if we just add things normally, so if the base 10 sum of the digits is even, then the base 7 number is even. You can see this, right? 0, 2, 4, 6, there's nothing to add up. But in the next row, it's 1, 1, which adds to 2, 1, 3, which adds to 4, 1, 5, which adds to 6. And then the next row, we're back to 0, 2, 4, 6 endings, where we have the first value of 2. So this is just kind of a divisibility rule that you can think of. And it does indeed work for this example above, right? Where 4, 3, and 0 add up to 7, which is odd. So that means that that number is odd at base 7. And you can do this for all bases and for divisibility by all of the different numbers. But this is a little bit more advanced. I just wanted to show you, so we, like I said, are comprehensive and still talk about these concepts in different bases, and that you can extend this to different bases. Just like we've extended the operations, you can extend divisibility rules to different bases. But that's all for section 5.1, and that's all for this video.